today I don't have any good formal notes for you guys because you've seen kind of all this basic stuff before. I just wanted to point out a few things and then we'll just get started. Up on the screen here I have an electrostatics equation summary. You actually saw this last year, or at least saw all the equations last year. So this is kind of a compilation of everything that you know so far in electrostatics. On the left side, what's the left-hand column?
Point charges.
Point charges, right. Thank you for reading. Yeah, it's only for point charges. Did you know that you could only use E equals KQ over D squared if you have a point charge? Or F equals KQ over D squared if you have a point charge? Did you know that?
Yeah.
Kind of begs the question, what's a point charge? Like, let's say I took this coffee mug and I charged it up. Is it a point charge?
No. It's a small particle.
So give me an example of something that we would model as a point charge.
Electron.
An electron, what else?
A proton.
A little circle thing, right. What? A proton.
The little circle.
Is a neutron a point charge?
No.
Oh, that's interesting. It has no charge, so I guess not.
Well, no.
Yeah. Basically, the deal with point charges is, and we're going to talk a lot about what you can and can't model as a point charge later. Just not today. But anything that's tiny could be modeled as a point charge. Sound good?
Yeah.
So a little pith ball or like a hunk of lint, right? Could be a point charge. Could a thread be modeled as a point charge?
No.
If you have a thread that's all charged up and is sticking to your clothes, is that a point charge?
No.
No. Is this balloon a point charge?
Could be.
That's a good question. We're going to talk about that much later. But yeah, these equations on the left are only valid for point charges. KQ over D squared. You can only use that if you have a point charge. If you have a plane or a sheet or parallel plates or something that's charged up, can you use KQ over D squared?
No.
No. What should you use?
The right side.
The right side, right. Only for parallel plates. Got it? Capacitors, right. So, delta V equals E times D. Ha! Interesting. Parallel plates. That's only for parallel plates. All right. What else is only for parallel plates? Capacitance. Actually, that's not true. We're going to talk about all that a little bit later. Stuff in the middle you can use for both. E equals the force per charge. The change in electrical potential energy from one place to another is Q times delta voltage. Q times the change of voltage. All right, fine. So that's just a quick equation summary of what you saw last year. So some other stuff to talk about. I got a balloon here. And there's an expression I like to use. It's called Herbin. Herbin. You guys know what Herbin is?
Nope. Humanoid Herbin.
Close. It's a head rub balloon is negative.
Wait, what? Where's the E?
H-R-B-I-N. Herbin. Head rub balloon is negative. You've never heard of this before?
No.
No. So I have a question for you. And by the way, I'm wearing a wool shirt today, so it works kind of like hair because my hair is not good. Why does that work?
Whoa, would you look at that?
Because I'm positive, right? I'm a positive guy, and I'm gonna attract the negative charge. Nice, I like that. Yeah, any negative Nellies in here?
Dino? Yeah, I would say Dino.
Dino? I can't even bring it close. Oh.
It's too hard. The force.
All right, so the question I have is, if I go like this, and I'm probably too short to do this. Oh, almost.
Raza.
Ah, darn
We
it.
need you to put it on the ceiling.
All right, let's get some more charge on here. So, there it is.
Oh, hey, what do you
Why does that work? Balloon's on the ceiling. Let's see, what's the charge on the balloon?
Negative.
Negative. What's the charge of the ceiling?
Neutral.
Ugh.
Neutral.
It's neutral! Why can a negative balloon stick to a neutral ceiling?
Because the negative charges are going to the ceiling that equal out.
So the negative charge, so the negatives from the balloon are touching the ceiling, making the ceiling negative, right?
It doesn't transfer to the ceiling.
It's kind of
Just
Wait, so the negatives in the balloon are touching the ceiling, making the ceiling negative, and therefore they should, oh crap, that would mean they're repelled. Is that what's happening?
no.
it's pulling the positive.
Wait, no, let's try this one. The negative balloons see all the neutrals in the ceiling say, yay! Is that what's happening? No. There's got to be something else going on here. What is it?
There's a bunch of positives and negatives in the ceiling.
And the negative of the balloon propels the negatives away, so the only.
Okay, everybody, what I want you to do is I want you guys to discuss this amongst your table, come up with an explanation, and while you guys are doing that, I'm going to pull up a website. This is the FET website, in case you guys don't remember what that is, fet.colorado.edu. They've actually started porting over some iPad simulations, and two of my very favorite iPad simulations are now on the FET website. So I'm going to go there now while you guys talk. Raise your hand if you think your table has an explanation of why a balloon will stick to the ceiling. Okay, so about half the tables are there. Okay, so what I've got here, if you go to fet.colorado.edu and click on the HTML5 link, that'll give you iPad-friendly versions of The Sims. And there's, not all of them are done, but some of them are done. This one in particular, which is one of my favorites. Why? Because there's a balloon and a sweater. And I just think that's really cool. So, they're awesome. Balloons are great. So I'm going to take this balloon, and what I'm going to do with the balloon, what I'm going to do?
You're going to rub it
I'm
against
going to rub it all on the sweater. What happens?
it. Gets a lot of negatives.
Ooh. Now, what happens when I let go of the balloon?
It's going to attract to that one.
It's going to go to the sweater.
Doink.
Boink.
Why?
Because there's no negatives.
Doink.
But if I let go here.
Negative. You're right. So if you take the balloon, so we know the balloon attracts to the sweater because the sweater's positive and the balloon's negative and opposites attract, right?
Yeah.
All right. However, does the balloon attract to the wall? Let's see. Whoa, let's bring it close. Oh, close but not touching. What do you notice?
The negatives in the wall are propelling.
What are the negatives in the wall called?
Negatives.
They're called electrons, right?
Yeah. Oh.
Right? They're called electrons. So what do you notice about, what are the positives in the wall called?
Protons.
Right, positively charged atoms, ions. Or, actually, no, that's not true. It's called protons. We'll talk about this in a second. But if you let go of the balloon, what's going to happen? Doink. Let's pull it off the wall a little bit. Let go. Doink. Doink. Ah, so the question is, why don't the negatives in the balloon do the same thing that the negatives in the wall do?
We talked about this last year. The balloon doesn't allow the motion or the electron. I only have two.
They actually do the same thing. However, there is such an excess of negatives in the balloon that even if the negatives in the balloon get pushed really far, the balloon is still an overall negative charge. Now, right now, what is the charge of the wall? What?
It's still neutral.
It's still neutral. It's still overall neutral. The wall is neutral. Because if you count the number of positives and negatives, what you'll find is there's still the same. I didn't lose any negative charges. They just pushed them out of the way to the right-hand side of the wall, right? It's still a neutral wall, but it's something called polarized. Raise your hand if you've heard that word before. The wall is polarized.
Equally divided.
Right? Do you guys know what polarized? Raise your hand if you know what the word polarized means from chemistry class.
Chemistry.
From a bio class, sure. Right? Polarized means what? Unequal distribution of charges. Means you got a positive side and a negative side. So back to the wall. So the wall line is overall neutral. Is that ceiling up there, that stuff that the ceiling's made of, the balloon is sticking to it, right?
Yes.
Is that conductor or insulator?
Insulating. I'm going to guess insulator, but I could be wrong.
Isn't it conductor? Because if it's an insulator, it's not.
Yeah, good question. So we're saying that a conductor is where the charges move and the insulator is where the charges can't move, right? Like balloon, conductor or insulator.
Well, air's an insulator, and so is rubber. So.
Right. The balloon is clearly an insulator. There's only a couple things. Give me an example of a conductor.
Water.
Copper. Right.
Actually, water's
Metal.
Yeah, not water as pure state, but you don't need.
Salt water. Why?
That's because salt molecules inside the water.
Is water, is H2O a conductor or an insulator?
No, it's an insulator.
It's a very, very effective insulator. I don't know if you knew that. Water does not conduct electricity hardly at all.
Yeah.
So what's the
Unless
pure water.
you dissolve something
What do we use?
in it.
Coca-Cola and water down.
You need to dissolve something ionic in it, like table salt.
That's why you don't want to be.
Right. If it's got ions dissolved in it, and people in AP Bio and AP Chemistry, is anyone in AP Chem in here? Okay, you know this. And AP Bio people? Just two people. You guys know that once you start dissolving stuff in water, the ions can then conduct electricity. And something that's not really a big deal in this class, but is actually a really big deal in general, there are actually two ways to conduct electricity. I don't know if you know this, right? You can conduct electricity via electrons or via ions. Like metal, for example. Are actual ions moving through the metal? No, what's moving through the metal? Electrons. Salt water. Are electrons moving through the salt water?
No.
What are moving through the salt water?
Ions.
Ions. That's interesting. Which do you think is less resistive of a flow path? Actually, the electrons. Why? Do you guys know? Raise your hand if you know what an ion is, or remember what an ion is.
Yeah.
It's a charged atom, right? Now, charged atoms can flow through water, right? Because if I think about this, if I put an electrical field, or I put a positively charged plate and a negatively charged plate here, and I have a bunch of positive ions in the water, what are they going to do? They're going to be attracted to one side, right?
Right. Yeah.
All right, so that's how that works. If I have a bunch of negatively charged ions, they're going to be attracted to the other side. That is a form of current flow. It's a form of electricity. It's ion flow rather than electron flow that happens in metals. All right? So in biology and chemistry, you talk a lot about ion flow. In physics, you talk more about metals, which is electron flow. But both of them count as current flow. Good?
Yeah.
All right. So back to this question. Is the ceiling conductor or an insulator?
Insulator.
It's an insulator. Okay? So how is this picture even possible where the electrons move? Because isn't by definition an insulator something where the electrons don't move?
Maybe the atoms are across.
Yeah. Did you know that atoms are made up of protons and electrons?
Yes.
Right? And guess what happens when you stick a big negative charge on one side of the atom? Kind of pushes the electrons over to the other side. Maybe not completely, but especially if it's a polar something like water, oh my gosh, you can really push the hydrogens over to one side and the electrons over to the other. Do you guys know that water is polar?
Yes.
Why is water polar? Yeah, has anyone ever drawn a water molecule before?
Yeah.
What's a water molecule look like if you draw it?
There's an H on the top, and then the O's go out of the triangle.
Okay, so water is how many protons in oxygen?
1. Oh wait, an oxygen.
8. Okay, so 1, 2, 3, 4, 5, 6, 7, 8. So that's the nucleus of an oxygen, right?
Yeah.
And then how many electrons around an oxygen? It's got to be 8, right, to be neutral? So first shell, there's 2 electrons. Next shell, there's, let's see, 1, 2, 3, 4, and 5, 6, right? So there's an oxygen atom. But the oxygen atom's not happy because it's not satisfying the octet rule. You guys remember that? So let's get it together with some hydrogens, right? Because if we do that, stick a hydrogen over here, and that hydrogen is going to share, and that hydrogen is going to share, and here's my oxygen sharing. What do we have? We have Mickey Mouse, right? That is a water molecule. And if you look, you squint your eyes real closely at this water molecule, what do you notice down around the chin of Mickey? Hella electrons. Right. Yeah, if you just cover up everything else, you'll notice Mickey's chin is very negative. But if you look up on the top side of the water molecule, what do you notice?
Very positive.
Very positive. So guess what?
Mickey Mouse isn't as happy as I thought.
Mickey Mouse is highly bipolar.
That's explain why you hit me.
He's got a positive side and a negative side. And guess what? Guess what would happen if you brought a Herbin, a negatively charged balloon, close to Mickey Mouse? His negatives would do what?
Move to the other side.
Negatives would repel and opposites would attract. And let's see, let's try it. Let's grab our balloon. All right. And I need some water.
Got them hops?
Oh, we're gonna do this where it bends the water.
Yeah, you can like water bend with it. Maybe that's how I'm turning.
Water bend? Wow.
Let's try this. We're going to take the balloon to the faucet and see what happens. Here we go, here we go, here we go.
First season was a lot better. No way. First season was a lot better.
Let's slow the water stream down a little bit, make this a little bit better.
Second season was cool.
Rubbing the balloon. Oh, look at that. Why is that happening? Oh my gosh. You see it?
It's because there's a full moon.
And if you're closer, you can see all the little droplets like going boing straight into the balloon.
So understood that.
All right?
Completely.
That is because water is
Polar.
polar, right? You now understand that, yes, we already know that positives can attract negatives, but we also saw from the balloon that positives can attract neutral. Why is that? And negatives can attract neutral. Why is that?
Because they just share the charge afterwards. The negatives from the neutral go to the positive, or the negatives from the negatives that go to the neutral.
You're taking whatever it is and you're polarizing the neutral, right? And then the negatives, the electrons repel the electrons, leaving positive closer, and the closer, well, let's look at this picture again. With the balloons, is it true that the negative in the balloon are attracting the repelling the negatives in the wall?
Yeah.
Is it true that the negatives in the balloon are attracting the positives in the wall?
No. The negatives are attracted to the
Okay, let me rephrase that. Is it true, because we're clearly weak on Newton's third law, Is it true that the negatives in the wall are repelling the negatives in the balloon?
Yes.
Is it true that the positives in the wall are attracting the negatives in the balloon?
Yes.
Yes.
So, therefore
So
the
who
negatives are
wins?
The positives.
Who wins? The positives or the negatives?
positives.
Depending on distance.
Oh, yeah.
The positives win. How come?
They're closer.
No, it's not because they're more massive.
They're closer.
The positives are closer to the negatives in the balloon.
The negatives are.
The positives in the wall are closer to the negatives in the balloon than the negatives in the wall are from the negatives in the balloon. Therefore, the positives win.
That's cool.
And therefore, doink, it attracts. And that's it for today.